Welcome back to the course entitled Symmetry, Spectroscopy and Applications. So, in the previous lecture, we were trying to discuss about the Newman projection, ring strain and cyclohexane conformation. So, we will continue our discussion in that direction. So, in the last class, we were talking about various conformations like staggered and eclipsed conformers. So, when we have understood that a staggered conformer is a low energy conformation and the eclipsed conformation is one of the high energy conformations, we will try to understand the same using some energy values. So, when you have drawn a Newman projection of ethane molecule in the staggered conformation like that, like the way I am drawing here, this is the most stable conformation of ethane. So, now if you rotate the back carbon by 60 degree, what we get is the eclipsed conformation, where the front carbon atoms, hydrogens on the front carbon are exactly behind, when the hydrogens on the back carbon are exactly behind the front carbon atom. So, as a result, what we end up getting is a conformation like this from the staggered conformation, which was like that. So, from the staggered conformation, we have come to the eclipsed conformation when these atoms are eclipsing one another. So, the strain that is generated due to this eclipsing of hydrogen 3 times, as you have 3 pairs of hydrogens, each of those is 4 kilojoules per mole. Which essentially means that this eclipsed conformation is 12 kilojoules per mole in energy higher than this one. So, if we assume this to be having the 0 energy or the lowest energy, the other one has the energy 12 kilojoules per mole higher. So, when we talk about this strain that is generated due to various orientations of the molecule, what we learn are there are different types of strains. The first type of strain is the steric strain, that is the destabilization due to the repulsion between the electron clouds of atoms or groups of atoms. They try to occupy the same common space. So, suppose for example, if I had 2 bromine atoms connected to the 2 carbon atoms on ethane, as I tried to show in your previous lecture, when these 2 bromine atoms are in the eclipsed conformation, there is a steric strain, because these 2 bromines are large enough to repel each other. The electron densities are very large on bromine atoms, and that creates a steric repulsion, and that gives you a steric destabilization due to repulsion. The next type of strain or destabilization is due to the repulsion between the pairs of bonds caused by the electrostatic repulsion of the electrons in the bond. So, this again happens when the bonds are in eclipse conformation or groups are in eclipse conformation. So, in this particular case, we have 2 types of strains. One is the steric strain because of those 2 bulky groups being eclipsed, and the bonds, every bond is behind another bond. CBr bond is behind CBr bond, this CH bond is behind another CH bond, this CH bond is behind another CH bond. So, every bond is behind another bond, and that the bond strain, that is called the torsional strain, is present in eclipsed conformation. The third type of strain is the angle strain or destabilization due to distortion of a bond angle from its optimum value. So, for example, in case of cyclopropane or cyclobutane, the carbon atoms are sp3 hybridized. So, by default we know that the carbon bond angles at the carbon should be 109 degree, but in case of cyclopropane or cyclobutane, that angle is no longer 109 degree, but it is distorted from that 109 degree. So, when we have different possibilities of molecular conformations, we should then try to identify them with appropriate nomenclature. So, when we try to draw the molecule in different ways, we see different conformations and we try to name them as anti, syn and gauche conformations. An anti-conformation is a description given to two substituents attached to adjacent atoms when their bonds are at 180 degree with respect to each other. So, that means, if I am considering this 1,2-dibromo-ethane, if the CBr bonds are opposite, so this CBr bond is up and that CBr bond is down. So, this conformation of this molecule is called the anti-conformation. Syn is the description given to two substituents attached to adjacent atoms when their bonds are at 0 degree with respect to each other. That means, when they are eclipsed, either this is eclipsed or this eclipsed, are different syn conformations. And the last type or third type is gauche conformation. Is given, this description is given to two substituents attached to adjacent atoms when their bonds are at 60 degree with respect to each other. That means, when it is like that. So, let us try to draw these different conformations in the next slide. The anti-conformation should be drawn like this. The syn conformation should be drawn like that. And the gauche conformation should be drawn like this. So, here the two bonds in anti are at 180 degree. Here the two bonds of CBr is at 0 degree, and here the two bonds about bromine are at 60 degree. So, now what if we ask you, if I ask you to tell me which conformer has the highest energy, which has lowest energy and which has intermediate energy, you should be able to quickly say that the anti-conformation has the maximum separation of bromine atoms, the maximum separation of bonds. So, this must be the lowest energy. The syn conformation has the minimum separation of bromines and bonds are eclipsed. So, this should be the highest energy, and this one should be having the intermediate energy. There is another different scene conformation that is possible, is this in this particular case of dibromoethane, where the bromine and hydrogens are eclipsed instead of all bromine, two bromines being eclipsed. So, this scene has slightly lower energy compared to this scene conformation, because here the bromine I am sorry for this incorrect drawing, this bromine and that should be separate. So, here in this particular case the bromine are far apart. So, there is no steric strain, it has only the torsional strain present. So, this has slightly lower energy compared to the other scene conformation. So, then when we have various different conformers that can be there for simple molecule like ethane. So, what we try to draw is a potential energy diagram for different conformers of ethane. So, in this diagram we draw energy on y axis and the torsional angle in x axis or the theta in x axis. So, when the torsion angle is 0, which means what we have is a fully eclipsed conformation. So, it has altogether 12 kilocalories per mole energy higher than the Gauss conformation, which is suppose at 60 degree appears here. So, the Gauss conformation would look like this. So, the energy would be somewhere here. If you rotate the molecule by another 60 degree and go to 120 degree, what we would get is something very similar to 1. So, the energy will be somewhere here. If you rotate the molecule, if you rotate the back carbon by another 60 degree and go to 180 degree, what we would get is very similar to number 2. And the corresponding energy will be same as number 2. And then if you rotate the back carbon by another 160 degree and reach 240 degree, you will again get the conformation 1, which is 12 kilojoules per mole higher in energy, and rotate the back carbon once again by another 60 degree, you reach 300 degree here. So, at 300 degree of rotation, the energy of the molecule will be same as 2. So, here it is again 1, there it is 2. And then again if you rotate the molecule by another 60 degree and reach 360 degree, we reach the molecule 1, the conformation 1 once again. So, these are the energy values for the conformation 1, those are the energy values of conformation 2. So, if I want to join these energies by a smooth curve, what I would get is like that. So, the potential energy of different conformers of ethane varies along this curve, and the difference between the highest and lowest energy conformer is 12 kilojoules per mole. So, this is called the potential energy diagram of ethane, and hope you are able to understand why this is like this sinusoidal curve. So, let us now see the different conformations of propane, and we will see here that the interaction energies or the torsion strains are different because of the presence of one methyl group. So, when we try to draw propane using the Shaw's representation, we write this and have a methyl group at the top position, and these two are hydrogens, when on the other side you have 3 hydrogen atoms. So, the corresponding Newman projection that one should draw is the following. The front carbon contains the methyl group, and there are 2 hydrogen atoms. The back carbon has 3 hydrogen atoms, which makes it propane. So, in this particular conformation, what we see is there is a torsional strain that appears because of the methyl and hydrogen being eclipsed, and that torsional strain results into 6 kilojoules per mole of destabilization energy, while as usual it was like in case of ethane, these 2 hydrogens, the torsional strains are 4 kilojoules per mole for each of them. So, overall, the total torsional energy that is associated with this conformation of propane is nothing but 4 into 2 plus 6 equal to 14 kilojoules per mole. If I rotate the back carbon by 60 degree, that means this hydrogen is rotated by 60 degree, we get the corresponding Gauss conformation, which would look like this. And we can now then avoid these 3 different torsion strains, and this molecule is supposed to be the lowest energy or zero energy conformation or the lowest energy conformation. So, when you try to draw the potential energy diagram like that for ethane we have drawn in the previous slide, the energy difference here will be 14 kilojoules per mole. So, if we try to draw the potential energy diagram, I will not draw for all the possible conformers, I will just draw 3 of them. Energy is plotted in y-axis as usual, and the dihedral angle theta is plotted in x-axis, and we will draw the positions with 0, 60, 120 and so on. So, when it is 0, as we have seen in the previous slide, the energy is higher. When it is at 60 degree, the energy is lower, and then again at 120 degree, the energy should be higher because again we get the eclipsed conformation, and in case of 180 degree, it will be again the same as the conformation at 60 degree. So, if you join these join these points with a curve, you would pass through minima at 60, 1 to 80, etc., and maxima at 0, 120, and so on. And the difference here is going to be 14 kilojoules per mole. So now let us move to the next higher alkane, which is butane. So in case of butane, let us first try to draw butane using the wedge and dash formula. The way I have drawn this is a C2 C3 bond is used as the middle point of the molecule, and then if I try to look at this molecule from this side, taking that C2 atom is in the front, so what we can draw is this. This is my front carbon. So there you have a methyl group, and then we have two hydrogen atoms in the front carbon, which are this and that. You see, when I am drawing from this side, this hydrogen comes here and that hydrogen comes there. That is on the right and left. Similarly, for the back carbon, I am drawing the methyl group, the other two hydrogens which are back to back. So this is called the fully eclipsed conformation or totally eclipsed conformation. So what we see here is the dihedral angle between the two methyl groups is 0 degree, and then slowly if we start rotating the back carbon by 60 degree, rotate the back carbon by 60 degree, the corresponding diagram for this molecule would be like this. And the Newman projection should look like this. This is called the Gauss conformation, where this torsional angle between the two methyl groups is 60 degree. The next possible conformation that we can think of is by rotation of this back carbon by another 60 degree. So in that case, what we would get is this conformation. So what we see here is that the methyl and hydrogen are eclipsed, and here the hydrogens are eclipsed. Unlike the first one, which was totally eclipsed conformation, this is partially eclipsed conformation, or we can call it as a simple eclipsed conformation. So here the angle between the two methyl group is now 120 degree. The fourth one that one can think of is by rotating this methyl group by another 60 degree, and you can draw the conformation like this. This particular conformation is called the anti-conformer, where the angle between the two methyl groups is 180 degree. If I ask you now to identify the most stable and least stable conformer, it will not be very easy to identify that without the values of the torsional strain and other strains that may be present in this particular molecule. But it can be guessed that in case of totally eclipsed, the torsional strain will be the maximum. So this will be the highest energy. And here we don't have any torsional strain, we don't have any steric strain. So this anti will be the lowest energy conformer. But to find out which one among these two is having a lower energy than the other, we need to know the values of these energies. So in the following lecture, we will continue from here and discuss about that Gauss interaction which is present here, and this particular interaction, we will talk about this interaction, we will talk about the energies that are associated with this kind of interactions, and we will try to then draw the potential energy diagram for N-butane various conformations.